It is. Einstein's theory of general relativity is our best theory of space and time. That if you put matter and or energy into that, then it curves it and distorts it, and it can stretch it and make it shrink. And so it's the response of space and time to matter and energy.
Daring to challenge one of the fundamental constants in the universe, we embark on a thought-provoking exploration. What if the speed of light is not constant? This inquiry takes us beyond the familiar bounds of Einstein's theory of relativity, inviting us to consider the implications of a variable speed of light. As we dive into this speculative realm, we unravel the potential impacts on our understanding of space, time, and the very nature of reality. This is Reveal the Mystery. If you're curious to learn mysteries of the world, space, and beyond, consider subscribing. Speed is a matter of perspective. If you accidentally drop your smoothie on a moving train, it may seem to descend straight down. However, from vantage point on the platform, the smoothie's descent appears diagonal, seemingly influenced by the train's velocity. Interestingly, when a laser beam is emitted from the train, everyone observes the same constant speed, 299,792,458 m/s in a vacuum, regardless of their individual speeds. The constancy of the speed of light is precisely articulated by something known as Lorentz invariance, serving as the foundational principle of special relativity. Einstein discerned that our measurements of distance and time must be relative to the observer, necessitating adjustments to maintain a consistent speed of light for all. This fundamental axiom is also integral to general relativity, where gravity is construed as a distortion of the space-time fabric. Rigorous testing has repeatedly affirmed the reliability of both special and general relativity without any discrepancies. It's crucial for scientists like us to uphold a dual stance of skepticism and open-mindedness, applying these mindsets to both established and emerging theories. Some scientists explore whether the speed of light could change, potentially altering the universe's fundamental aspects. This idea challenges traditional physics, as the speed of light isn't just about light, but governs information travel. Altering it would affect the essence of space-time. Defining units like meters and seconds rely on the speed of light, complicating the consideration of a variable light speed. Einstein asserted that time is what clocks measure, implying it gauges the universe's rate of change. Slowing the speed of light, a fundamental constant, and results in a proportional slowdown of time. This principle extends to all matter, from atoms to clock gears, where the speed of light dictates the rate of internal change, influencing time's flow. In special relativity, altering the speed of light impacts both space and time, although such changes are imperceptible in our daily experiences. Exploring the potential consequences, we consider whether a change in the speed of light could reshape the relationship between space and time, particularly at the quantum level. Back in 1957, a smart scientist named Robert Dicke suggested something called the variable speed of light, or VSL. He wondered if gravity might happen not because space bends, but because the speed of light slows down near big things. Imagine how light changes direction when it goes through something slower, like a lens. Dicke thought gravity might work similarly. He guessed that since time goes slower in a heavy place and slowing light also slows time, maybe a changing light speed could be a good idea. In 1957, there were only a few tests for a big theory called general relativity, and some results could match with both curved space and a changing light speed. But now, we have more proof that shows space and time are dynamic. Things like spinning masses, twisting space, and crashing black holes making waves don't fit with the idea of light speed changing. Even though Dicke's idea was interesting, it doesn't fit with the latest evidence. If Dicke were around today, he'd probably agree with what we know now. Even if a changing light speed doesn't fully explain gravity, could it still have some role to play? There's a strange thing about our universe that might be explained by this idea. If we look towards the edge of the universe, we can see there's warm, smooth gas from before stars or galaxies formed. And we see the same thing in every direction. Early on, the universe was very similar everywhere, almost the same temperature and density everywhere. This suggests that all that stuff must have been close together at some point to share energy and end up the same. The issue is, given how fast the universe is expanding, there wasn't enough time since the Big Bang for those regions to have talked to each other. We've explored the horizon problem previously, typically resolved by cosmic inflation. This theory suggests that initially, distant regions were connected, exchanging energy at the regular speed of light and reaching a uniform temperature. The universe then underwent a rapid expansion, surpassing the speed of light before slowing considerably. This expansion caused once closely aligned regions to drift apart, creating the illusion of no prior connection. Another perspective proposes linking distant points by having light travel faster in the past, maintaining unity during the universe's expansion. If light then decelerated to its current speed, distant regions would appear detached. If accurate, this notion implies a gradual decline in the speed of light, potentially explaining galaxies appearing to recede faster. However, theories suggesting changes in light speed face challenges in elucidating the precise alterations needed to emulate both inflation and dark energy. Currently, cosmic inflation stands as a more coherent and widely accepted explanation. In 1992, John Moffat's variable speed of light theory addressed the horizon problem by suggesting about a 10 circumflex 30 ms speed of light in the early universe. Similar concepts by other physicists proposed energy-dependent light speed. Although intriguing, no observed differences in light speeds with varying energies have been found. Testing these ideas is challenging due to their predicted outcomes resembling general relativity. These ideas are intriguing, but can we test them given that variable speed of light (VSL) theories predict the same outcomes as more conventional ideas in general relativity? Another method to investigate changes in the speed of light is by examining its impact on physics. The speed of light plays a role in many physics laws, including the fine structure constant defining electromagnetism's strength. If the speed of light changed, one would expect this constant to change as well. However, there's no evidence supporting such alterations. While this doesn't conclusively prove the speed of light has never changed, it strongly suggests minimal changes over billions of years. The challenge for VSL theories lies in their apparent violation of physics principles, particularly Lorentz invariance, crucial for maintaining a logically ordered universe. Disrupting Lorentz invariance can result in conflicting interpretations of events among different observers. Moreover, a variable speed of light undermines the fundamental charge parity time (CPT) symmetry, implying that the laws of physics appear distinct based on the direction of time. This is problematic as CPT symmetry is believed to be fundamental, with no observed instances of its breakdown. There are some ways to address these objections. For instance, we can think about the change in the speed of light not being a fundamental thing, but more like how light changes when it goes through water. So, what if the thickness of space, like the way light moves through water, changed over time? However, for this idea to work and slow light down enough to solve a specific problem, the increase in this thickness would have to be really, really big. This change would also have to affect all types of light and even gravitational waves, which is different from how regular materials act. While this is one way to approach the problem, it's not the usual way, and there are some other complicated ideas to consider. But to understand and accept these alternatives, you'd need to be really committed to these ideas. Currently, there's no evidence supporting a fundamental change in the speed of light, and it may not be a meaningful concept. This depends on our incomplete understanding of the quantum nature of space and time. It's valuable to revisit the foundational principles of our successful theories. Any new theory must match or surpass the predictive power of the old one. While challenging to challenge the internally consistent relativity, clashes with quantum mechanics permit ongoing questioning. This extends to examining whether the cosmic speed limit is unalterable or if information travel speed in space-time can change.